What direction am I coming from here? We're interested in a world where there's billions and billions of data sources. And every building, every door, every car, every cell phone, every machine is going to be ability to sense data and send it someplace. And we think we can take advantage of that data and do interesting things with it. So this is a story about lots of data sources streaming to online models. Then from those you get predictions, anomalies, and actions making, I'll tell you some applications a little bit later. The scaling problem we're interested in is one of billions of data sources and millions of models. We're not talking about large data sources. In fact, we're not even storing the data anywhere. We're just streaming it and throwing it away. But we think this is going to be a very prevalent case throughout the world in the coming years. There's lots of things you need to do to make a world where you have millions of models that are programmatically created, that humans have not touched, that are doing useful things. I'm going to talk primarily about two key criteria today, that is online learning and high-order sequence memory, just to make sure we're all on the same page here. When I talk about online learning, we're talking about the fact that we're building models with no training sets, no test sets. You have a stream record by record. You have to infer and build models at the same time, and nothing's being stored anywhere. High-order sequence memory refers to the fact that very often the patterns in the data are temporal patterns. It's like melodies, songs, things like that. You've got temporal patterns, and very often to make the best prediction, you might have to go back 2, 3, 5, 10 periods ago in your data set. You don't really know. So to really do a good job of this, you have to have high-order sequence memory. These are hard attributes to do in programmatically created models. The agenda for my talk is I'm going to talk about briefly, this is a short talk, the brain is a streaming analytics engine. I'm going to talk about the representation used in brain, sparse distributed representations. I'm going to talk about how you build a high-order sequence memory of sparse distributed representations, how you make it online, and I'm going to show you a little bit about a product we built that does all this. Okay, our goals, surprisingly, it had nothing to do with data. My company, Numenta, it was the goals of the company to develop discover principles of operation in the neocortex and build systems that operate on those principles. And I say systems, it's going to be software and hardware. We've made a lot of progress on this, and you say, well, what does that have to do with streaming data? Well, it turns out that the brain is a great streaming data engine. If you think about your neocortex, you've got a bunch of sensory arrays. The retina is really a million sensors. You have this high-velocity data stream that's streaming into your brain right now. When you were born, your neocortex didn't know anything. They had to build models of the world from that data. Again, nobody had a training sets, test sets, and things like that. It just has to do it on its own. So how can we do that? I'm going to tell you, as I said, we've learned a lot about how the neocortex works, especially in the last 2 years. Tremendous progress. I'll just give you I'm going to give you the top 3 highlights and dig into them a bit. So the first thing is, this is something we've known for a while, that the neocortex itself is a hierarchy. It's a hierarchical memory system. It's physically constructed that way. And so this is an array of memory regions that are all doing something similar. The thing they're all doing is they're all doing sequence memory. So they're all learning patterns in time, and they're all making predictions, and they're all doing anomaly detection. And we kind of have a pretty good idea how this hierarchy in sequence memory works. And then the whole system is built on sparse distributed representation, so that's the data that's being stored in these sequence memories. Our goal is to build a system that works on these principles, but we didn't. When we started building all this stuff, and we were modeling all of it. We found that we could do something very significant without the hierarchy. By just modeling one section of neocortex, we could do actually quite a bit of interesting stuff, and it made our software much, much faster. It made it practical for commercial applications. So we're going to do that. We're going to build a system that basically models one layer of the neocortex for doing streaming data. So the goal would be something like this. We have on the left, we have some fields, records are streaming in, one or more fields at a time. Those can be numbers, categories, text, dates, times, whatever. We're going to put them through an encoder. We're going to create sparse distributed representations. We're going to create a sequence memory of them. And from that, we're going to make predictions and detect anomalies. All right, let's jump into my first topic. What is a sparse distributed representation? It may or may not know this, so let me just go through it quickly. A sparse distributed representation is a representation that has lots of bits. We typically, and very few of them are active. Our typical representation we use are 2,000 bits long, and 2% of the bits are active, so 40 active bits. But these are sort of the very large bit streams, not streams, but large collections of bits. Now the key thing about sparse distributed representations is that each bit has semantic meaning. It has some meaning in the world. If I ask you what the third bit in an ASCII representation is, it means nothing. Right? Here, on a sparse distributed representation, it has some attribute of the things I'm trying to model. And what I do is I pick the top 2% of those attributes to represent my object. This is how brains work. And so we have this very long bit stream where we have the top components that represent a particular object that are active and all the rest are 0. So there's 3 things we need to know, 3 operations or properties of sparse distributed representations you need to know to build a sequence memory. First of all, if you just compare 2 of them bit by bit, if they have a common bit in the same location, that means they're sharing semantic meaning. This doesn't happen by chance, so I very quickly can take any 2 representations and find out what attributes they have in common and where are they different. And I do that just by a bit-by-bit comparison. The second thing is, what if I wanted to store one of these guys and then see if it occurred again later? Well, you don't store the whole bits, you don't store all 2,000 bits. You just store the indices of the bits that are on, the active bits. So in this case, in our representation, we're going to store 40 bits. And that's great. If I see those 41s again, I know I've got my pattern. That's the one. Now, for various reasons, efficiencies and so on, we actually can get away with something much simpler than this. We can subsample. Instead of storing all the indices of all the bits that are on, we can just pick some subsample. In this case, I said, let's say I'll store 10 of them. And I'll say, if I see those 10 bits, I'm going to say my pattern was there. Well, you can say, well, I might get a failure there. I might discover 10 bits that were actually part of another pattern that I wasn't storing. That's true. It actually happens very, very rarely. And if it does happen, you're recognizing something that is semantically very similar to the thing you did store. And so it is good enough. And the brain does this continuously. We're going to take advantage of this property. The final property is you can form a union of these representations. You can literally just OR them together. So if I took 10 sparse distributed representations, each with 2% of the bits active, and I form a union of them, OR them together, I'll have a new representation, which is approximately 20% of the bits active. Now, I can't undo that, but I can do something very, very useful. I can ask if a new unknown sparse distributed representation is in the member of that first 10. And all I have to do is by saying, well, okay, if every one in my new thing has a corresponding bit on in the union, I'm going to say it was in a member of the first 10. Again, you could say, hey, that could result in an error. I could be doing mixing and matching. I could be picking some bits from one of the patterns and some bits from another pattern. It's very simple to do the math on this. You can show that that doesn't happen. It's so rare, you can essentially assume it's never going to happen. A lot of interesting properties come out of sparse distributed representations. It takes a while to get used to thinking about them. Okay, so there's our sparse distributed representations. How are we going to form a sequence memory of this? We're going to go back to the brain. One slide on neuroscience. Sorry about that. Here's a picture of the neocortex. If I zoom in on one little section here, you'll see that the cells are arranged in these layers. If I zoom in on one of these layers, I see these little dots which represent the neurons. They're all packed in there very tightly. There's 2 basic organizational principles going on in here. There's a vertical one, a columnar one, which all those cells that are vertically aligned on top of one in very narrow little columns, they tend to respond to the same pattern from an input point of view. They all have the same feed-forward response properties. But the vast majority of the connections are across these columns, horizontal connections like this. If you look at any particular one of these cells, this is a typical cortical pyramidal cell here, the most noticeable thing about it is it has a profusion of processes called dendrites. These are those little things sticking off the cell body here. And all the connections to the cell are along those dendrites. And these are the synapses along here. So these little guys here are the actual synapses along a section of the dendrite. Now, we've learned something a couple of things very, very important about neurons in the last 15 years. And one of the things we've learned is that these, along the dendrite here, there's some very strong nonlinear properties. And basically what will happen is if I have a series of synapses within a short distance, they all become active at the same time, it can generate a spike on that dendritic segment. It becomes like a coincidence detector. It says if I see these 10 synapses active at the same time, or these 20, or something like that, literally those kind of numbers, it can cause the cell to fire. And we're going to take advantage of that. So there's many of these dendritic segments all over the cell. We're going to model this. We're going to model this with essentially a set of artificial neurons. This is showing an array from one of our simulations, which has got 4 cells per column. These different colors represent different activation states of the cells. Our artificial neurons are much more complex than the ones you're used to seeing from other models. I won't go into all the details, but just look at these blue dots here. This little row here, each one of these is like a dendritic segment. It's like a coincidence detector. They're connected to other cells. You'll see how in a moment. And if a number of these connections are active over some threshold, then this cell will fire. And so there's a series of these dendritic segments that are being ORed together to make that neuron do its thing. All right, so the question we want to answer now is, how does that structure and those neurons learn sequences, and how does it learn high order sequences, and how does it do it online? Okay, how does it learn sequences? let's just array our bits in our sparse distributed representation as if they were cells in a layer like this. So these are maybe, this is not quite 2000, but pretend it is. These are all of our bits in our sparse distributed representation. The ones that are active are these red guys. Now, at any point in time, I got some pattern here coming in, and next time I have another pattern coming in. It's changing rapidly all the time. You can imagine this is going on in your brain right now, millisecond to millisecond, while I'm talking to you. It's really cool. And what we want to do is we want to learn these sequences of these patterns. We want to learn how to learn what to anticipate is going to happen next. And the way we're going to do that when a cell becomes active, like this cell, what it's going to do is it's going to look for the cells that were just previously active before it became active, and it's going to form connections to it. It's going to say, okay, when I became active, there's a bunch of other cells nearby that were active, and I'm going to form connections to that. It doesn't have to look at all of them. It can subsample from the local neighborhood, and that's good enough. And it's going to try to predict its own future activity. Every cell does this. And what will happen is, if you learn, after you've exposed the system to a series of patterns, what you'll get is you'll have a new input like these red cells, and there'll be a whole bunch of patterns that are simultaneously being predicted in the next instance. So if I learn the pattern A is followed by B, and then A is followed by C, and A is followed by D, when I see A, I will predict B, C, and D. So this is a multi-step prediction, these yellow cells. It's a union of predictions. Now, this is pretty cool, but the problem is it's only a first-order memory. I can only make a prediction based on the previous state. There's no context carrying forward, and so it really doesn't solve our problem of being a high-order sequence memory. We're going to solve that problem by going to this columnar architecture, adding more cells per column, and I'll illustrate how that works on this slide here. These two sparse distributed representations are the same, and so the same bits that are on and off here, and we're basically going to associate a 10 cells, if you will, above each bit. And if a cell if a bit is 1, we basically say that column is active, and we're going to pick one of the 10 cells up here. And I won't go into how we do this, but you can just start off by random. They're going to get learned. But so this one is going to be represented by that cell. Here, this pattern is the same pattern, but at a different instant, I'm going to pick a different cell to represent it. And so you can say, well, so I have different ways of representing the same input. So we have here, if I have 40 active bits and there's 10 cells per column, there's 10 to the 40 ways to represent a particular input in different contexts. There's a tremendous number of ways you can represent the same pattern. So think about this. I'm going to say the word 2, like there are too many 2 2s to count. I said the word 2 multiple times in different contexts. You didn't get them confused. Your brain is able to sort through them because it's representing the same pattern in different ways in different contexts. And that's basically the mechanism we're going to use. And we're going to use the same sort of thing when a cell becomes active. It's going to form connections to other cells nearby. I hope you can follow that. It's a very short talk. I can't go into more detail here. But when we built this, we've been building these for years now. You form a memory of sequences doing this way. It's very high capacity. You can store lots of patterns. You can store very, very deep, high-order patterns if that is what's required. You can make multiple simultaneous predictions. And I didn't show this at all, but you can do semantic generalization. That's because using that property I mentioned earlier, if I've learned a sequence of patterns, and now I see new inputs coming in that are semantically similar but different, but semantically similar, I can relax my threshold constraints, and I can use the patterns I've observed before to semantically similar new inputs. And we do this all the time in our brains. Okay, so that's the high-order sequence memory. The question now is, how do I make it online? How do I make it learn continuously? Now think about it. Imagine I have a system that's trained. It knows all the patterns in the world. And a new pattern comes in that's novel, hasn't seen it before. Well, it could be noise. Very often it is noise. But I can't ignore it. In an online system, I don't have time to go back later and say, oh, statistically, I know there wasn't noise. You have to. Whoops. What happened there? Sorry about that. System was recorded. I just destroyed. You have to basically learn on every record before you know whether it's noise or change in the world. So the way we're going to do this is pretty simple. We're going to say, look, I have to train on every record, but if a pattern does not repeat, I'll forget it, and if a pattern does repeat, I'll reinforce it. And we have to do this anyway, because in these streaming world, we have so much data that's coming in. Over time, we have a capacity to our system. We have to forget things that don't occur again and again. So how are we going to do this? We're going to look at the way the brain does this again. Go back to our system here. We have these cells that are predicting their activity. They're doing by forming connections on these dendritic segments. And these are modeling what is really going on in the neuron, the synapses on the dendritic spine. Now, one thing we've again learned in recent years people used to think, and most people still do think, that learning occurs in the brain by changing the strength or the weight of the synapse. That's not true. It's going to take us a while to get over that. Turns out the synapses form and deform or disappear rapidly. You can watch these movies of them, it's incredible. So we can form new synapses in the order of a minute or less. And really the training in the neural system is the formation of synapses, the growth of synapses, not the strength of synapses. And that's where the primary learning is going on. So learning is the formation of connections. And we can, when a connection forms, it literally grows slowly, and you can, by reinforcing it, grows. So we're going to model that. Our connections have what we call a permanence, which is a scalar that goes between 0 and 1. And this is reflecting sort of the growth of a new connection. If a connection is above some threshold, we'll say it's connected, and if it's below, it's unconnected. So our synapses, our connections are binary, they're not scalars. They're binary, it's either 0 or 1, but we have a scale of permanence which allows us to train. So when we train something, we'll be incrementing or decrementing the permanence of the connection, not the strength of the connection. And that's basically all it takes to do online learning. Okay, so we've built a product that uses this. This is not a product pitch, but you'll get a sense for how this works if I show it to you. It's called Grok. It's currently in private beta, but there's some information on our website about it. It's a prediction engine for streaming data. It uses all these principles I just talked about. We basically take streams of data. This could be multi-fields, one or more fields, any kind of data that you can encode. I won't go into how we do the encoding. That's pretty interesting and fun stuff to talk about, but I don't have time for it today. But you can take these fields, you stream them into this, run it through encoder, you get a sparse memory, you run it through our sequence memory, which is typically 2,000 cortical columns, 60,000 neurons. We then put out predictions and detect anomalies. We can do this very, very rapidly. We spend a lot of time optimizing this in software. What does a user do to the user system? Basically, there's a programmatic API. But the big problem is you have to define your problem. What am I trying to predict? How often do I want to predict it? How far in advance? I might be sampling like an energy usage in a building every 5 minutes, but I want to predict my energy usage 4 hours from now. And you end up with different models depending on how often you want to predict and how far in advance. You also need to specify an error metric. There is no single error metric that is correct for all problems. The error under the ROC curve is not useful. You actually have to say what are the business values of false positives and false negatives, and this will impact how we build our models. Then the user has to create a data stream. Basically says, here's a bunch of fields that I can stream to you. Here's what the field types are. They can combine it with public data sources that we have, like weather and Twitter streams and things like that. And then what Grok does in a process I won't have time to tell you about, it basically determines the best that it can find. There's almost an infinite number of models that could be built on the data, so we basically do a best within a certain amount of resources. It determines which of the fields it should use, one or more, to solve the problem, how to encode those fields. It even does record aggregation if required. So maybe you're collecting every minute, but you're trying to predict every hour. Maybe every minute is too often, so we'll do aggregation of that. And what you get out of it is you get out one or more predictions at any point in time. You'll say, okay, you wanted me to predict this 3 hours in advance. Every time you give me a new record, I'll give you a new prediction. If there's more than one prediction, it gives you probabilities on it. And it learns continuously. We're applying this to many different types of problems today, but we're still discovering where it's best fit for people doing energy pricing, energy demand, product forecasting, ad network returns, machine efficiencies in server farms. It was mentioned earlier this morning's talk about how much energy used in these server farms. There's ways you can improve that by predicting what applications are going to be running, server loads, things like that. Let me just show you a couple of slides showing you what this looks like. This is some data from a gymnasium in Australia. That's energy consumed, electricity consumed in this building throughout the day. They measure it every hour. The blue line is the actual, the red line is a prediction. I believe this is predicting 4 hours in advance, but you can't see it. I'm almost done. And you can see that there's actually in terms of daily patterns here. There's actually, these guys are smaller in width. That's because they're Saturday and Sunday. Grok picked that up, and it's doing a pretty good job. You actually can't tell if Grok's doing a good job by looking at a picture like this. It can be very, very misleading. It looks pretty good. But you have to really get into the details of the data to know if it's doing something valuable. But let's just assume for the moment it's okay. Here's the same data a little bit later on the same vertical axis, and you notice that the building all of a sudden is consuming a lot more energy, and the patterns are slightly different. We don't know why. Maybe more people are going to the gymnasium. Maybe it's a holiday. I don't know. But Grok has to adjust it right away. The whole point of this is that no one has to know what's going on. It just does the right thing. A few more slides here just to show you what this. Look on the right-hand side here. These are our 2,000 bits. At any point in time, we have some of them being active from feed-forward activation. A green dot in this case means that this was an input that occurred from feed-forward, and it was predicted. So this is a perfect prediction at any point, at one point in time in this graph. Exactly what happened was exactly what was predicted. Here's a situation where we had multiple predictions going on. The little blue circles are other predictions that did not occur, but notice the green dots are still saying, well, what did occur was a subset of that, was one of the predictions, and it was correct. Here's a situation where Grok didn't do so well. The red dots are essentially things that occurred from a feed-forward input. This is what the current data says, but they were not predicted. So this is either an error, an anomaly, something like that. But notice here that some of the things were predicted correctly. So when we say it's an anomaly or not an anomaly, it's not a binary thing. This is really an ensemble model when you get down to it. It's a little bit, you can make analogies between random forests and things like that, but it's an ensemble model. You have actually a pretty sophisticated way of saying how much of an anomaly was this, what aspects of this were anomalous and which aspects were not anomalous. A lot of fine control can go on in that. So in summary, we believe in a future where there's billions of data sources, many millions of models that are being programmatically created in making the world more efficient and making predictions, anomalies, and actions. The necessary capabilities of doing this are high-order sequence memory and online learning. The neocortex suggests a robust solution to this using sparse distributed representations and there's distributed sequence memory. And if you want to, we have a commercial implementation of these principles. It's currently in private beta. There's a white paper on our website which talks about some of what I talked about, but not all of it. The basic algorithms are in there. And there's some pseudocode and some other people around the world have implemented versions of this. So that's the end of my talk. Thank you.
Thanks for the talk. I was wondering if Grok is predicting how well Grok is going to do in the future. A question that I had was, once you've sort of done your prediction, you have your metrics as well you've done, how do you gain some insight into what are the important, essentially, features? So in a random forest, you could go back and say, what are the features that are showing up most often? Is there a way to sort of do the introspection on the learned model to pull out what's actually important? Because that then derives, how people wind up, interacting with the data.
Yeah, yes, it can. There's a process where they can go through here, with the process of discovery of the factors, which factors and how to encode them. And so there's a long history of that. And if you want to look at that history, you can. So we can rank all the factors and say how they relative strength. It's kind of and so you can go back and look at that if you want to see what helped and what didn't help. What's hard to do is at any point in time say, well, how did I make this prediction? I mean, you can do it, but it's really, you have to really dig in deep to figure that stuff out. If someone says, hey, exactly how did I get to this point? How many steps in history did it take to get here to make this prediction? It's all in there in the data structures, but it's not easy to get out of it. It takes some graduate students or something to do that kind of work. But from a very high-level point of view, a programmer is typically the one who uses this product, not a machine learning expert necessarily. And you can get back a report, basically, which factors were helpful and not helpful, and why Grok included them or didn't include them.
Any other questions? Your example on the Australian gym with Grok, how well would you have done if you just guessed that power consumption and this time bin would have been the same it was a week before? How much better did Grok do that?
Yeah, so we have a question. Everyone hear the question?
Yeah.
Okay. Yeah, the question, basically how much better did you just did the week before? Well, I can even say, well, what if I just asked how much better it did than it did the moment before? Imagine if I highly sampled the data, by sampling every second. Well, the new data point is almost certainly going to be very, very close to the previous data point. You have to be very careful of these things. So we have a series of what we call trivial predictors or trivial answers, and we're always testing ourselves against them. Your question presupposed some knowledge about this as a weekly pattern. We didn't know that. We don't know that. We don't go in knowing that. So you can always go back to the fact that if you know the underlying causes of the data, you can always come back and say, well, how did you discover this and how did you discover that? The point of this is to discover that on its own. Is it true that it's a daily pattern? I don't know that. Grok doesn't know that either. So anyway, you do have to be careful. But the point is, you don't, if you take a machine learning expert and look at any data source, and you spend, take any of your graduate students, you put them on it for a few months, they're going to come up with a good solution. The point of this is automating it and making it so that you don't need those resources, that you can do this rapidly and low cost. So if it turned out
that maybe you just look at last week's production and that's a great prediction. Might be, I don't know. It still might be valuable to just have to figure that out for you. And if it changes, it'll figure it out anyway. I mean, it's like you don't want to encode that knowledge into the system because it may not be true in the future. So, but in this case, it actually isn't true. But in this particular case, the gym, these guys are machine learning people. They've been working on it for a year. We did much better than they could have done. They had done up to that point in time. Not that saying you couldn't have done better than them. I don't know. Our claim isn't like, this isn't about, yes, there's a whole bunch of people saying, our algorithm is better than so-and-so algorithm, our algorithm is better than so-and-so algorithm. I'm not into that. I'm into, can you do this stuff rapidly, low cost, and do a great solution and build an answer for someone, but it has to be online and it has to be high-order models. And most techniques out there don't do a very good job of that. Any other questions? Yes?
On what platform, device, or sort of construct does Grok live?
Yeah, Grok today lives on Amazon Server Cloud. It doesn't have to. The actual inference of a model is very fast. It can be run on a single CPU. The determining of the factors and the analysis of the data, if you want to, how to encode it, that we actually do in a very highly parallel fashion. So that's required, but you can imagine this stuff getting embedded in different types of environments. But today, for convenience and for most of our customers, we're using a cloud-based service. Did you have a further question?
So you're considering
Are we considering occasionally connected scenarios? Today,
for instance,
well, like an offshore oil rig being one that's not connected, you're saying? Okay, well, actually, we're working with an offshore oil rig, and it is actually amazingly connected. Literally, it's one of our customers.
the new ones are.
Yeah. Well, okay, so there's a general question about, yes, we have the latency of connectivity, but again, the algorithm itself say nothing about the delivery mechanism. So today we're delivering this as a cloud-based service. Maybe that's the wrong choice. Maybe we'll have to embed it in something else. We'll have to make a local versions of it. What if we find there's also a problem with data security? We're working with some people doing credit card fraud detection. So, there's issues with that. We've got some HIPAA compliant problems we're dealing with. There's a whole series of issues. So I just talked about the algorithm itself. The delivery of the algorithm can be done in many different ways. Grok today is a software service on the cloud. We typically doing the frequencies that are anywhere from like once every second to once a day. We don't do anything less than that. And but we're not doing things down in the millisecond range. Although the algorithm theory could do that, just that you wouldn't be able to do that in a cloud-based delivery mechanism. Yeah. One more question?
One more question.
How do you deal with noisy data, missing data, and data that are in just different units, a voltage stream and a temperature stream that just don't have any natural normalization meaning to each other?
So those are separate questions. Noisy data is not a problem. With a true online learning system, it handles noisy data. It starts learning it, and then if it doesn't occur again, it forgets it. So that's really not an issue at all. Missing data, it depends. That's very much a problem specific. For example, do the records have a timestamp or not? Some do, some don't. You can clearly get confused. For example, if I was trying to recognize a melody and I drop out a few notes in the middle, I might lose track of the melody I'm listening to, and Grok can do the same thing. However, if I start up again, Grok will just the same way. It'll say, okay, here's some new data where I'm going to pick up again a pattern in the middle of the sequence. You don't have to start it. You can start anywhere, and it just sort of picks it up as it goes. So it depends. It's very different on the different types of data sets. And the last part of your question was, what was it?
Pieces that are naturally
Oh,
normalized.
the pieces that are not naturally normalized. I don't quite understand that. It really gets into the, maybe you can tell me the question offline later, but it really gets into how do you do the encoding. And I didn't talk about that. But we take a number, and essentially we encode it the way the cochlea encodes things. We essentially assign a whole series of bits to it. Each bit is representing an overlap bucket of values. So on a number scale, you can have these overlapping buckets. And so at any point in time, you have a series of bits that are on. And if your number moves a little bit, then some of the bits change and some of them don't. So two numbers that are close on the number scale we're going to have similar representations. And the ones that are farther apart will have no overlapping bits. We don't care about what it means. We just say, okay, the data's coming in. These are the ranges I've seen so far. Here's how I'm going to try to bucketize it into these sort of bit patterns. It makes no difference what it is. And we don't know, but we can handle categories very well, binary and non-binary categories. In fact, you can do some very clever things. If you know the semantic meanings of your categories, you can do custom encodings. So you can say that category A and B are similar in these ways, and category B and D are similar in these ways. You can get some generalization principles out of that. For example, when we take a date, one of the things we do is we look for weekend and weekdays type of thing. We just take a date, but Friday, is that a weekend? Friday night, is that a weekend or weekday? Well, it's a bit of both. So we encode that. That's part of it. It's not a binary decision in there. So I can talk more detail about it if you want later. Okay.
All right. Senator Peter.
You have a stream record by record. You have to infer and build models at the same time, and nothing's being stored anywhere. High-order sequence memory refers to the fact that very often the patterns in the data are temporal patterns. It's like melodies, songs, things like that. You've got temporal patterns, and very often to make the best prediction, you might have to go back 2, 3, 5, 10 periods ago in your data set. You don't really know. So to really do a good job of this, you have to have high-order sequence memory. And these are hard attributes to do in programmatically created models. The agenda for my talk is I'm going to talk about briefly, this is a short talk, the brain is a streaming analytics engine. I'm going to talk about the representation used in brain, sparse distributed representation. So what direction am I coming from here? We're interested in a world where there's billions and billions of data sources. And every building, every door, every car, every cell phone, every machine is going to be ability to sense data and send it someplace. And we think we can take advantage of that data and do interesting things with it. So this is a story about lots of data sources streaming to online models. Then from those you get predictions, anomalies, and actions making, I'll show you some applications a little bit later. The scaling problem we're interested in is one of billions of data sources and millions of data streaming into your brain right now. When you were born, your neocortex didn't know anything. They had to build models of the world from that data. Again, nobody had training sets, test sets, and things like that. It just has to do it on its own. So how can we do that? I'm going to tell you, as I said, we've learned a lot about how the neocortex works, especially in the last 2 years. Tremendous progress. I'll just give you I'm going to give you the top 3 highlights and dig into them a bit. So the first thing is, this is something we've known for a while, that the neocortex itself is a hierarchy. It's a hierarchical memory system. It's physically constructed that way. And so this is an array of memory regions that are all doing something similar. Representations. I'm going to talk about how you build a high-order sequence memory of sparse distributed representations, how you make it online, and I'm going to show you a little bit about a product we built that does all this. Okay, our goals, surprisingly, it has nothing to do with data. My company, Numenta, it was the goals of the company to develop discover principles of operation in the neocortex and build systems that operate on those principles. And I say systems, that's going to be software and hardware. We've made a lot of progress on this, and you say, well, what does that have to do with streaming data? Well, it turns out that the brain is a great streaming data engine. If you think about your neocortex, you've got a bunch of sensory arrays. The retina is really 1 million sensors. You have this high velocity data stream of models. We're not talking about large data sources. In fact, we're not even storing the data anywhere. We're just streaming it and throwing it away. But we think this is going to be a very prevalent case throughout the world in the coming years. There's lots of things you need to do to make a world where you have millions of models that are programmatically created that humans have not touched, that are doing useful things. I'm going to talk primarily about 2 key criteria today. That is online learning and high-order sequence memory, just to make sure we're all on the same page here. When I talk about online learning, we're talking about the fact that we're building models with no training sets, no test sets,